Thank you very much. Now, welcome to this
Excuse me.
class. Hello?
Excuse me.
Yeah,
Excuse me.
yes.
Yesterday you didn't send the recordings
I
of the
did.
yesterday.
I did.
You did.
Yes, I did.
Okay. So
Are there
thanks.
any witnesses?
I didn't receive on my side. That's why I just wanted to confirm.
I have put in both groups, okay?
Okay. So,
Yes.
sir, thanks.
Okay. So now we move on based on from what we have. Please, Wanyonyi, do you have a question? Yep. Okay. From the chemistry you have studied so far, you can easily identify two types of ways in which a chemical bond can form between atoms. Atoms are involved in chemical bonding, and the reason why they get involved in chemical bonding is because the way they are not stable, because they do not have octet of electrons. So they'll be engaged in chemical bonding in order to have octet of electrons. They form a bond. The chemical bond that will be formed between two elements could be as a result of transfer of electrons, or it could be as a result of sharing of electrons. When a chemical bond is formed as a result of transfer of electron, the chemical bond, as you know, will be ionic. Then it will result in ionic compounds where you have fully positively charged and fully negatively charged species involved in the chemical bonding, as in the case of sodium chloride. An electron is transferred when sodium chloride is formed. An electron is transferred from the sodium to the chlorine. The sodium has lost electron while the chlorine has gained electron. Then as a result of that, the sodium will be positively charged while the chlorine will be negatively charged. I don't know where the echo is coming from. Zainab, you have to mute unless you have a question. Do not unmute. Okay? So we can have chemical bonding formed through either transfer of electrons or sharing of electrons. When it's formed through sharing of electrons, it is covalent. When it's formed through transfer of electrons, it is ionic. When an ionic bond is formed, the two atoms that are involved in the ionic bond will be charged. One of them will be positively charged, the other one will be negatively charged. The other type of covalent chemical bond is the one that is formed as a result of sharing of electrons, and this one is covalent. Because of bad manners of some of your classmates, I have disabled your ability to unmute, okay? And covalent bond is formed by sharing of electrons. And then we know, because of the position of carbon in the periodic table, and because of also its electronegativity, carbon can only be involved in covalent bonding. The bonds carbon forms with other elements are as a result of sharing of electrons. Okay, but sharing is never the same. And as a result of that, the bond that is going to be formed will be polar. not non-polar, but polar covalent bonds will be formed. So let me just give you as the scenario so that you understand what polar and non-polar covalent bond is. If you look at the cartoons you see here, on your left, you have a tug of war between two hydrogen atoms, between identical atoms. And they are holding on and pulling the electrons of the bond, the two electrons of the bond towards themselves. But since the tug of war is between two people that have the same strength, the same physical fitness, there is not going to be a winner. Okay, so even in this particular case, as you can see, the chemical bond is between two identical elements, between two hydrogen atoms. The two hydrogen atoms have equal share of the two electrons of the chemical bond. None of the hydrogen has a higher share of, a larger share of the electrons. So this covalent bond that is formed between the two hydrogen atoms is non-polar. There is no polarization. Polarization means one center has excess, the other center has deficiency. Polarization in politics means this type of people have this kind of view and these other people have this very extreme view. Even on BBI, we have different views. There are those who totally opposite. There are those who totally support it. Polarized views. Okay, but when you have a covalent bond between two identical elements or elements that have the same or nearly the same electronegativities, the electrons of the covalent bond will be shared equally. So as a result, you will not see one center having excess of electron, the other center having deficiency of electrons. The electrons will be shared equally. Such type of covalent bond is non-polar covalent bond. However, if you have a covalent bond between two different elements, like between chlorine and hydrogen, it's like a tug of war between one person who is very big and strong and another weak person. There is no way this weaker person will have a good share of the electrons. So in this particular case, we have a covalent bond between chlorine and hydrogen, two different elements. Then as you can see, the chlorine has pulled the electrons of the bond towards itself. The hydrogen is hardly holding on to these electrons. As you can see, most of the rope is towards the chlorine. The hydrogen is just hanging on it. So in this case, the electrons of the bond are more on the chlorine than they are on the hydrogen. On the chlorine, we'll have excess of electrons, while on the hydrogen, we'll have deficiency of electrons. You remember, if this was an ionic bond, an ionic bond, for example, between sodium and chlorine, the chlorine would take the electron, the chlorine will be fully negatively charged, and the sodium will be fully positively charged. But in this particular case, it's not an ionic bond. It is a covalent bond, which is formed by sharing of electrons. The hydrogen brought one electron, the chlorine brought another electron. The two of them formed a chemical bond. But once the chemical bond is formed, one of the elements, the more electronegative element, in this case chlorine, will pull the electrons of the bond towards itself, but it does not have strength enough to take away both electrons from the hydrogen. If it has the strength to take away both electrons from the hydrogen, the bond would have been ionic bond. But in this case, it is covalent. There is a share. The only difference is the share is not the same. One of the element will have a larger share of electrons than the other. So on the chlorine, we'll have excess of electrons. On the hydrogen, we'll have deficiency of electron. There will be a center on the chlorine where there is excess of electron. There is another center on the hydrogen where there is deficiency of electrons. So the bond is polarized. Such type of covalent bond is called polar covalent bond. So we have two types of covalent bonds, two extreme type of covalent bonds, non-polar and polar covalent bonds. Whether there is going to be the covalent bond is going to be non-polar or polar will depend, as we shall see, on the differences in terms of electronegativity between the atoms that are involved in the covalent bonding. If they are the same, if the two elements that are involved in covalent bonding, they are the same, like in the case of a covalent bond between two hydrogens, the electrons are going to be shared equally. Therefore, the covalent bond will be non-polar. But if you have a covalent bond between two elements that are not the same, two elements that have significant difference in terms of the electronegativity, the electrons of the bond are not going to be shared equally. So the bond, the covalent bond that is going to form between such element is polar covalent bond. And as you can imagine, the majority of the chemical bonds that exist in organic compounds is between different elements. Most chemical bonds are between different elements. So the most common covalent bond you'll find in organic molecules is polar covalent bond. So polar covalent bond, you can represent it by a tug of war, as you can see here, between two different people. One is very, very big and stronger, and another one very, very small and weak. If there is a tug of war between the two, obviously most of the rope will be towards the bigger and stronger person. The bigger and stronger person will have a larger share of the rope, while the weaker person will have a smaller share of the rope, polarized. Okay, so whenever you have a covalent bond between two elements, and these elements are not identical, and these elements, most importantly, have different electronegativities, the covalent bond that's going to be formed between them will be polar covalent bond. So let's talk about polar covalent bonds. Before we do that, let's talk about the other type of covalent bond, non-covalent bond. If you have atoms with equal or nearly equal electronegativities. If such atoms form covalent bonds, these two elements will have equal attraction for the electrons that are involved in the chemical bonding. For example, if you have a chemical bond between two hydrogen atoms, a chemical bond between two nitrogens, and a chemical bond between chlorine atoms, since this chemical bond is between identical elements, the electrons of the chemical bond, the electrons of the sigma bond in hydrogen, the electrons of the sigma and the 2 pi bonds in nitrogen, and the electrons of the sigma bond in chlorine will be shared equally between the atoms. When you have a chemical bond between identical elements or between elements that have nearly equal electronegativities, the electrons of the bond are going to be shared equally. For example, if you look at the distribution of electron density in these molecules, since these are molecules that have identical elements bonded to each other, the electrons of the bond will be uniformly distributed. Such type of covalent bond is non-polar covalent bond, no polarization. The electron density is distributed equally between the two atoms. None of the atoms will have a larger share of electrons. So such type of compounds are non-polar. There is no center which is either positively charged or negatively charged. There is no center that is partially positive or partially negative. The distribution of the electrons is uniform. Such type of molecules, you should expect them to have a uniform distribution. As a result, they are neutral, okay? The distribution of the charge is uniform. However, most chemical bonds are between two elements that are not the same. So if the two atoms that are combined through covalent bonding are different, then there will be an unequal sharing of electrons. One of the elements will have a larger share of the electrons than the other. And then the reason why one of the elements will have a larger share of electrons than the other is because of their electronegativities. So when you have a chemical bond between two elements, and these two elements are different, the elements have different degree of attractive force for the electrons of the covalent bond. One of the element will have more affinity or more power to attract the electrons of the bond towards itself than the other. When such happen, we'll have a chemical bond, a covalent bond that does not have a uniform distribution of charges. So the reason why the electrons of the bond between two different elements are not going to be shared equally is because the two elements have differences in terms of their electronegativities. One of the element has a higher electronegativity than the other. So electronegativity is a measure of the tendency of an atom to attract bonding pair of electrons towards itself. Electronegativity measures the ability or the or the tendency of an atom to attract electrons of the covalent bond towards itself, to pull those electrons of the covalent bond towards itself. That's what electronegativity measures. It measures the tendency of an atom involved in a chemical bonding to attract the electrons of the bond towards itself. So elements that are not identical will for sure have different electronegativity, different tendencies to attract the electrons of the bond towards themselves, resulting in a non-polarized bond. So there is a scale for the electronegativity of the elements. The elements in the periodic table have different electronegativities. There's a scale that is developed for electronegativity, and the most commonly used scale for electronegativity is called the Pauling scale. Then in this Pauling scale, fluorine, the most electronegative element in the periodic table, is given an electronegativity of 4.0. So fluorine, the most electronegativity element, has an electronegativity of 4.0, and the electronegativity values range from 4 all the way to 0.7. So elements, the alkali earth elements, the lithium, sodium, potassium, cesium, francium, like this, those ones have the least electronegativities, while fluorine, chlorine, bromine, iodine, like that, those ones have the most, they're the most electronegative element. So electronegativity varies from the most electronegative element, fluorine, which has got an electronegativity of 4.0, to that of cesium and francium, which have electronegativity of 0.7. So if you look at the periodic table, the electronegativity varies following a certain trend. So as you go from left to right in the periodic table, electronegativity increases. As you go from lithium, beryllium to boron to carbon, nitrogen, oxygen, fluorine, like this, as you go like that from left to right, electronegativity increases. We are not considering the halogens because the halogens hardly involve in any type of chemical bond. So we don't worry about their electronegativity. As a result, the most electronegative elements are the ones that you find on the right of the periodic table. And then the other way in which electronegativity varies in the periodic table is as you go up or as you go down a group, electronegativity decreases. So the most electronegative elements are the ones you find at the top of the periodic table. So as a result of these two trends, electronegativity increasing across a period, therefore the most electronegative element is the ones that you find in the right. The elements that you find in the extreme right of the periodic table are the most electronegative element. Then the other one is electronegativity decreases as you go down a group or increases as you go up a group. Therefore, the most electronegative elements in the periodic table are the ones at the right of the periodic table and the ones that are at the top. So as a result of this, you see, fluorine is the most electronegative element because it is at the extreme right of the periodic table. It is also at the top in a group in a periodic table. So fluorine has an electronegativity of 4.0, And then the second most electronegative element in the periodic table is oxygen, which has got an electronegativity of 3.5. And the next one is nitrogen, which has got an electronegativity of 3.0, and then chlorine, which has got an electronegativity of 3.0. Okay, and then if you look at carbon, carbon has an electronegativity of 2.5, while hydrogen, the most common element to which carbon is bonded to, hydrogen has an electronegativity of 2.1. So what I want you to remember and have a rough idea is that the electronegativity of carbon is 2.5, and that of hydrogen is 2.1. The most electronegative element is fluorine. It has got an electronegativity of 4. And then the second most electronegative element in the periodic table is oxygen with an electronegativity of 3.5. And then chlorine is the next one, chlorine and nitrogen, both of which having an electronegativity of 3.0. It is really not important you cram these numbers, not at all. But you have to understand how electronegativity changes in the periodic table. For example, if you have a chemical bond between carbon and oxygen, if you have a chemical bond between carbon and oxygen, when you look at carbon and oxygen in the periodic table, you'll find carbon and oxygen are in the same period of the periodic table, and then oxygen is to the right of carbon. Therefore, you should expect between carbon and oxygen, oxygen must have a higher electronegativity than carbon. Therefore, if you have a covalent bond between carbon and oxygen, since oxygen is more electronegative than carbon, and therefore oxygen has got higher tendency for the electrons of the bond, oxygen will pull the electrons of the bond towards itself. So on oxygen, we'll have excess of electrons. On the carbon, we'll have deficiency of electron, resulting in a polarized covalent bond. So you can easily tell in what way a chemical bond is polarized, since you have a rough idea of the position where these elements in the periodic table are found. For organic chemistry, you do not have to know the position of all these other elements. If you know just the first 20 elements in the periodic table, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and the neon, then sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. And then as you go down here, fluorine, chlorine, bromine, iodine, like this. If you just know these ones, you can easily tell how the bond is polarized. Okay? So in covalent bond, with substantial difference in electronegativity, the electrons involved in bonding are not shared equally. The most important thing you have to know is that the two atoms involved in the covalent bonding must have substantial difference in terms of electronegativity for the chemical bond, or for the electrons involved in the chemical bonding not to be shared equally. But if the two elements that are involved in covalent bonding, despite the fact that one is more electronegative than the other, but so long as the differences in electronegativity between them is not significant, that chemical bond is not going to be polar. Because you pull towards yourself, I also pull towards myself, and then we can have small difference in terms of our size and strength, but we are not really very far off from each other. As a result, if there is a tug of war, between two people that have almost similar strengths, there is not going to be winner. So for a covalent bond between two elements to be significantly polarized, there must be reasonably substantial difference in terms of electronegativity. So in covalent bonds with substantial difference in electronegativity, the electrons involved in the bonding are not shared equally. The more electronegative atom will have a greater attraction for the bonding electrons and therefore takes the larger share of the electron density. For example, if you have a chemical bond between hydrogen and fluorine, fluorine has got an electronegativity of 4. Hydrogen has got an electronegativity of 2.1, 2.2. 4 minus 2.2, 2.1 is about 1.8, which is a significant difference. But if you have a covalent bond between carbon and hydrogen, the electronegativity of carbon is 2.5, the electronegativity of hydrogen is 2.2. The difference in terms of electronegativity between hydrogen and carbon is not significant. One of the elements does not have significantly more attraction for the electrons of the bond than the other. As a result, the hydrogen-carbon bond can almost be nonpolar. So there must be significant difference in terms of electronegativity for the covalent bond to be polar. So for example, if you have a chemical bond between hydrogen and fluorine, remember when I showed you this covalent. So let me see if I can allow you to unmute. Okay. Then if all of you behave, I will keep it like that so that you can ask questions, okay? I don't like a situation where I lock you out. I don't like it. But if people disturb, what can we do? Okay? So if you have a covalent bond between two elements, and these two elements have differences, significant differences in terms of electronegativity, the electrons of the bond are not going to be shared equally. One of them will have a larger share of the electrons than the other. However, if the two elements that are involved in chemical bonding do not have any difference in terms of electronegativity, that means a covalent bond between identical elements, or a covalent bond between two elements that have almost identical or similar electronegativity, the electron of the bond are going to be shared uniformly. So as you can see here, when you have a covalent bond between two identical elements, the electron density is shared equally between the two atoms. It has got a uniform distribution. So you can have the hydrogen on this side, the other hydrogen on this side, or the chlorines. In such case, the electron distribution is uniform. Such type of covalent bond is nonpolar. But if the chemical bond is between two different elements that have significant differences in terms of electronegativity, one of the elements will have a larger share of the electrons, as in the case of hydrogen fluoride here. As in the case of hydrogen fluoride, this is a covalent bond between hydrogen and fluorine. Fluorine is more electronegative than hydrogen. So fluorine, as a result, has a higher tendency to pull the electrons of the bond towards itself more than the hydrogen. As a result, on the fluorine will have excess of electrons. On the hydrogen will have deficiency of electrons. As a result, such type of bond is polarized. Okay, as you can see, the electron negativity of hydrogen is 2.1, that of fluorine is 4.0. 4.0 minus 2.1 is 1.9. It is a significant difference. As a result, the electrons of the bond, the electrons of the covalent bond are not going to be shared equally. The more electronegative elements, in this case fluorine, will have a larger share of the electrons. So as a result, on fluorine we'll have excess of electrons. On the hydrogen we'll have deficiency of electrons. They can only have excess or deficiency, partially excess or partially deficient, because this is not ionic bond. If it was an ionic bond, one of them will be fully negatively charged, the other one will be fully positively charged. But this is covalent. Covalent is sharing. But it's just that sharing is not the same when the two elements that are involved in covalent bonding are not identical, and more importantly, they have significant differences in terms of their electronegativity. So when you have a situation, what results is a polar covalent bond, a bond with an even distribution of electron density. The electron density distribution will be uneven. One of them will have a larger share of electron than the other. Okay, so how polarized a particular bond is dependent on, most importantly, the differences in electronegativity of the atoms that are bonded. For example, in this particular case, we have a covalent bond between hydrogen and fluorine. This covalent bond is polarized. You can also have another type of covalent bond, a covalent bond between hydrogen and chlorine, for example. When you compare the polarity of hydrochloric acid and the polarity of hydrofluoric acid, their polarities are not the same. HF is more polar than HCl. The reason being the differences in terms of electronegativity between fluorine and hydrogen. 4.0 minus 2.1 is more than the difference in terms of electronegativity between chlorine and hydrogen. 3.0, which is the electronegativity of chlorine, minus 2.1, which is the electronegativity of hydrogen. 3.0 minus 2.1 is 0.9. But in the case of HF, the difference between the electronegativity of the fluorine and the hydrogen is almost 1.9. Therefore, HF is more polar than Cl. So one of the most important factors that determines the degree of polarization of a bond is differences in electronegativity between the atoms that are involved in chemical bonding. The more the difference, the more polarized is the bond. So the degree of polarity of a bond particularly depends on the differences in electronegativity of the two atoms bonded together. The most important factor that determines the polarization of a bond is the differences in terms of electronegativity between the atoms that are involved in covalent bonding. The more the difference, the more polarized the bond. And then the other factor that determines the degree of polarization of a chemical bond between two atoms is the size of the atoms that are involved. The more an element that can easily be more polarized than an element which is dense and small. So there are two factors that determine the degree of polarity of a covalent bond. The most important one is differences in electronegativity. Sometimes you can look at a covalent bond, and then based on the electronegativity difference between the two atoms, you might say this one is more polar than the other. But when you look at the experimental data will tell you the other way. When such happens, you have to take the size of the atoms that are involved in covalent bonding. I will give you assignment on this so that you try to figure out and understand this. Once you have submitted your assignment, we'll have a tutorial class to discuss this. But the most important thing I want you to know that the degree of polarization of a bond depends on differences in electronegativities. The larger the difference between the electronegativity of the atoms involved in the covalent bonding, the more polar or polarized the molecule is. The other factor is the size of the atoms. So the degree of polarization of chemical bonds are not the same. As we have seen, the covalent bond between hydrogen and chlorine and the covalent bond between hydrogen and fluorine are not the same in terms of their polarization. The covalent bond between hydrogen and fluorine is more polar than the covalent bond between hydrogen and chlorine. Okay, such type of covalent bonds that are formed between two elements that have differing electronegativities is called polar covalent bond. So if you have a polar covalent bond, a covalent bond between hydrogen and chlorine, as you can see in this particular case, the chlorine, it has got very big teeth. It looks very, very aggressive, and the hydrogen is scared and sweating, barely holding on to its electron. Such type of bond is polar covalent bond, very highly polarized. On the chlorine, we'll have excess of electrons. On the hydrogen, we'll have deficiency of electrons. It is like a tug of war between two people who are significantly different from each other in terms of their size and strength. So the bigger, more stronger one will have a larger share of the rope compared to the smaller and weaker one. Okay, now on one of the elements of a polar covalent bond, we'll have excess of electrons. On the other element, we'll have deficiency of electrons. The one that has got excess of electron is somehow negative. The one that has deficiency of electrons is somehow positive. They are not fully positively charged or fully negatively charged. They are only partially positive or partially negative, because still remains that the bond between the two elements is covalent. It's not ionic. It is only in ionic situation where you have the two elements having full charges. In sodium chloride, we have sodium, which is fully positively charged, and chlorine, which is fully negatively charged. But in covalent bond, we cannot have fully positively and fully negatively charged species, but one of them will be partially negative, the other one will be partially positive. There is going to be partial charges on the atoms that are involved in covalent bonding, and partial charge is given using this symbol delta. So if you have a covalent bond between hydrogen and fluorine, on the fluorine we'll have deficiency of electrons. On the hydrogen we'll have deficiency of electron. On the fluorine we'll have excess of electrons. So the hydrogen will be an electron poor region, while the fluorine will be an electron-rich region. So there is excess of electrons on the fluorine and deficiency of electrons on the hydrogen. To show that, symbolically, we put partial charges. The way in ionic bond, we put sodium plus, chlorine minus. We put positive and negative charges. To show how a bond is polarized, we put partial charges. We put partial positive and partial negative. So this is how we show the polarization of the hydrogen fluorine bond. The hydrogen is partially positive, while the fluorine is partially negative. Okay? On the fluorine, we'll have excess of electrons. On the hydrogen, we'll have deficiency of electrons. To show this, to show how a bond is polarized, we put partial charges, partial positive and partial negative. Polarization of a bond is a big deal. It's very, very, very important. One, for example, if you react hydrochloric acid with a hydroxide minus OH, with minus OH, this minus OH is going to react with which one? Will it react with the hydrogen or will it react with the fluorine, the minus OH? Will it react with the hydrogen and form a bond with hydrogen, or will it form a bond with the fluorine? When you react HCl, hydrogen, it will react with the hydrogen because the hydroxide ion is negatively charged, minus OH. Opposite charges attract. That's why when you react HCl with sodium hydroxide, the minus OH of the sodium hydroxide will come and form a bond with the hydrogen, take away this hydrogen of the HF. It will not come to the fluorine. So polarization of a bond is very, very important. It will tell us how a chemical bond is going to form, between which element and which element we are going to have a chemical bond. Okay, so however, if we were to react hydrogen fluoride with something that is positively charged, the positively charged species can only be attracted to the fluorine and not to the hydrogen. Okay, and then as we shall see in a short while, that polarization of a bond has got significance in when it comes to determining which particular molecule is high boiling, which one is less boiling. Because what will determine the boiling point, what will help us determine which molecule is higher boiling than the other, is the forces that hold the molecules together. If molecules of the same attract to each other very strongly, it is very difficult to boil off such a liquid. But if the force of attraction between them is weak, they can easily boil. So when you have a polar covalent bond, a molecule that is polarized, this molecule and its other sisters will align themselves such that the positive and the negative centers, they face each other. So there's going to be an electrostatic attraction between the fluorine of one HF molecule and the hydrogen of another HF molecule. Then if you want to boil this, you have to overcome the force of attraction between the hydrogen and the fluorine, between the positive center and the negative center. So polarization has got significance in terms of reactivity of the molecule, in terms of even their physical state, whether they are going to be liquids, solids, or gas. Even when they are a solid, whether they are going to be high melting or low melting, etc. this polarization has a very important role to play. Therefore, you have to take your time and understand the concepts and put the partial positive and the partial negative center where they belong. So one way of showing the polarization of a bond is to put partial positive and partial negative charges on the partially positive on the electron pull center. You put partially positive. On the electron rich center, you put partially negative. The element that will be partially negative will be the more electronegative element. So you look at hydrogen and fluorine. Hydrogen is on the left side of the periodic table. Fluorine is in the extreme right of the periodic table. There is very big difference in terms of electronegativity between hydrogen and fluorine. Therefore, on the fluorine, you put partially negative. On the hydrogen, you put partially positive. The other way of showing the polarization of a bond is by the use of a crossed arrow. We have two ways of showing the polarization of the bond. One of them is to put partially positive and partially negative. The other one is to use a crossed arrow. So this is an arrow, and arrows have got a lot of meaning in chemistry. So this particular arrow is a crossed arrow. You have an arrow, then on this side you have a cross. So this is a crossed arrow, and the crossed arrow starts from the positive center, from the partially positive center, and points towards the partially negative center. So this is how we show how a covalent bond is polarized. You should be able to identify which one is the positive center and the negative center. And then you start the arrow from the positive center and let the arrow indicate towards the negative center. And then you put across a line on this one. It shows how a covalent bond is polarized. It will show us the nature of a polarized covalent bond, which is the positive center, which one is the negative center. We show that by using partial charges. We also show that by using crossed arrow. Okay, so you can identify any chemical bond, a chemical bond between two elements that are not identical. And then based on their position in the periodic table, you can easily tell which one is more electronegative than the other. And then you can show this by putting partial positive and partial negative charges as well as crossed arrows. Okay, so another way of representing the different electron density within a molecule is by a crossed arrow. And then this crossed arrow points from the partial positive end of the molecule towards the partially negative end of the molecule. Okay, so let's continue on this. Now, you remember what we said, that there are two basic types of chemical bond between two elements. And these are covalent and ionic. And then we say whether a chemical bond between two elements is going to be ionic or not will depend on the position of the elements in the periodic table. If you have a chemical bond between the alkali metals, like sodium, lithium, which are on this extreme left of the periodic table, and the chemical bond between the halogens that are on the extreme right of the periodic table, that chemical bond that will form between such element is ionic. Okay, and then we saw also we have covalent bond, and covalent bond is formed usually between elements that are in the middle of the periodic table. Okay, but we can also know whether a chemical bond is going to be covalent or ionic based on the differences in terms of electronegativity between the atoms that are involved in chemical bonding. Now, if the electronegativity difference between the atoms that are involved in chemical bonding is more than 2.1, very big difference, this chemical bond between the two elements is definitely ionic. The difference between the two elements in terms of the attraction they have, the affinity they have for the electrons is very significant, that one of the elements end up taking the electrons completely, becoming negatively charged, fully negatively charged, and then the other element from which the electrons are taken away from becoming positively charged. So if the electronegativity difference between two elements is big, greater than 2.1, the chemical bond between the two elements is ionic. Other than that, the chemical bond will be covalent. The difference will not be significant for one of the atoms to take away the electrons. So differences in electronegativities, delta En between two elements involved in chemical bonding determines whether the bond is ionic or covalent. It is a difference in terms of electronegativity between the two elements will determine whether the chemical bond is going to be ionic or covalent. So if the electronegativity difference is greater than 2.1 and greater, the chemical bond between the two elements will be ionic. However, if the electronegativity difference between the elements that are involved in the bonding is less than 2, the chemical bond will be covalent. And then, of course, in covalent, we have seen two extreme types of covalent: non-polar and very polar or strongly polar. So we have non-polar covalent bonds, weakly polar covalent bond, strongly polar covalent bonds. So if the electronegativity difference between the atoms that are involved in chemical bonding is 0, that means if the two elements that are involved in chemical bonding have identical electronegativities, the two elements will have equal attraction for the bonding electrons. So such type of a chemical bond between such elements will be non-polar covalent bond. So it will be non-polar covalent bond. But if the electronegativity difference between the two elements that are involved in chemical bonding is between 0.1 and 1, if you take the difference in terms of electronegativity, you subtract the electronegativity one from the other, and then if you find the difference is between 0.1 to 1, that covalent bond is polar, but it is weakly polar. However, if the electronegativity difference between the elements that are involved in covalent bonding is between 1.1 and 2, the covalent bond is strongly polar. For example, we've seen in HF, fluorine has got an electronegativity of 4.0. Hydrogen has got an electronegativity of 2.1. 4.0 minus 2.1 is 1.9. A very big difference, but all the same, less than 2. As a result, HF is a strongly polar molecule. However, if you look at HCl, the covalent bond between hydrogen and chlorine, chlorine has got an electronegativity of 3. Hydrogen has got an electronegativity of 2.1. 3.0 minus 2.1 is 0.9. So as a result, HCl is weakly polar, while HF is strongly polar. So differences in electronegativity delta En between two elements involved in chemical bonding determines whether the bond is either ionic or covalent. If delta En is greater than 2.1, the bond is ionic, and if it is less than 2, it is covalent. Then among the covalent bond for non-polar molecules, the delta En is 0. For weak polar molecules, the change in electronegativity is between the difference in terms of electronegativity between the atoms is between 0.1 and 1, while for strongly polar molecules, the change in electronegativity is between 1.1 and 2. Okay, so depending on the differences in electronegativity between the atoms that are involved in chemical bonding, you can tell whether the chemical bond between the two is ionic or covalent. Then when it is covalent, whether it is non-polar, weakly polar, or strongly polar. Is it okay?
Yes.
Hello?
Yeah.
Yeah.
Huh? Okay. Is it clear?
Yes. Yeah.
Okay.
Yeah.
Good. Asante. Now, what we have done so far, we have just qualitatively said one bond is more polar than the other. Qualitatively, we just say this one is more than the other. But there is a quantitative way of measuring polarity of a molecule quantitatively. And then this is done by measuring the dipole moment. So the dipole moment is nothing but a tool for measuring the polarity of a molecule. So molecules that have higher dipole moment are more polar, and molecules that have zero or very small dipole moment are either non-polar or weakly polar. So dipole moment is a measure of the polarity of a molecule. It is something that you can determine experimentally. The dipole moment is a measure of the polarity of a molecule. The more polar the bond, the higher is the dipole moment. So for example, so this the dipole moment is measured in unit of debye, T pronounced as debye. So we can say the dipole moment of this bond is 1.1 debye, it is 2.5 debye, etc. So let us see the dipole moment of some common bonds. You remember what determines whether a particular bond is going to be more polar than the other? The most important factor that determines that is the differences in terms of electronegativity between the two atoms involved in the covalent bonding. So if the electronegativity difference between them is small, they are less polar. If it is more, they are more polar. So now let's look at this element, these chemical bonds. A chemical bond between hydrogen and carbon, hydrogen and nitrogen, hydrogen and oxygen, hydrogen and fluorine. Let us look at these chemical bonds. We have fixed the hydrogen, then we are changing the element to which the hydrogen is bonded to, and then we are determining them, we are changing them in a predictable way. We are changing them from carbon to nitrogen to oxygen and fluorine. From on the periodic table, after carbon, we have nitrogen, then oxygen, then fluorine. So we are going progressively to the right of the periodic table. As we do that, Who is this who was unmuted? When I teach third year students, etc., nobody unmutes. I thought you guys are not children. Okay? You are university students and you know what it means. Okay? Do not unmute unless you have a question. Okay? So let's look at the hydrogen carbon, the hydrogen nitrogen, the hydrogen oxygen, and the hydrogen fluorine bond. As you go from hydrogen carbon to hydrogen fluorine, as you go down, the electronegativity of the element to which the hydrogen is attached to is increasing as you go from carbon to nitrogen to oxygen and to fluorine. What it means, the polarization of the bond is increasing as you go from hydrogen carbon to hydrogen nitrogen to hydrogen oxygen to hydrogen fluorine. Polarization of the bond is increasing. Therefore, the HF bond should be more polarized than the HO, which should also be more polarized than the HN, which should be more polarized than the H carbon bond. This is reflected in the dipole moment. Dipole moment is a measure of the polarization of a bond. Therefore, the hydrogen carbon bond is less polar compared to the hydrogen nitrogen bond, which is less polar than compared to the hydrogen oxygen bond, and which is less polarized, less polar than the hydrogen fluorine bonds. Therefore, we should expect the dipole moment, which is a measure of the polarization of a bond or the polarization of a molecule, to increase like this. And then when you go from HF to HCl, bromine, and iodine, we are going down a period in the periodic table. As you go down a period, electronegativity decreases. As a result, the difference in electronegativity between the hydrogen and these halogens decreases as you go down the period. Therefore, HF should be more polar than HI, which you can see here. HF has a dipole moment of 1.7. This one has got a dipole moment of 1.1. This one has got a dipole moment of 0.8. This one has got a dipole moment of 0.4. The same when you fix carbon. This is, we fix the hydrogen and we change the other element here. We fix the carbon and then we change. So in this particular case, the chemical bond is between two carbon atoms. There is no electronegativity difference. As a result, this chemical bond between the two carbon atoms is non-polar, which is the case because the dipole moment is 0. But if you go down, carbon, nitrogen, oxygen, fluorine, progressively the carbon is being bonded to more electronegative element. So as a result, as we go down, the polarization of the bond should increase, since dipole moment is a measure of polarity. As you can see, the dipole moment increases from 0 to 0.2, 0.7, and 1.6. And then if you go from CF to CCl to CBr to C iodine, as you go like this, you'll see electronegativity of the element are increasingly decreasing. Therefore, as you go down, the dipole moment should decrease, which is the case here. For CF, it is 1.6. For carbon chlorine bond, it is 1.5. For the carbon bromine bond, it is 1.4. For the carbon iodine bond, it is 1.2. Okay, so the more polarized a bond, the more the dipole moment. The dipole moment is not the same as the differences in terms of electronegativity. It is not. Okay, you remember for HF, the difference in terms of electronegativity between fluorine and hydrogen was 4 minus 2.1, it was 1.9, but this is 1.7. Between chlorine and hydrogen, chlorine was 3, hydrogen was 2.1. 3 minus 2.1 is 0.1, but the dipole moment is 1.1. So the dipole moment is not the difference in terms of electronegativity between the two elements, which, as we shall see in a short while, because dipole moment has got two factors that influence dipole moment or polarization of a bond. One is electronegativity difference. The other one is the size. So the dipole moment takes into consideration, as it measures the polarity of a bond or the polarity of a molecule, it takes both factors into consideration. It takes the size factor as well as the differences in electronegativity. So that's why you see that the dipole moment is not the same as the differences in electronegativity between the two atoms. All the same, dipole moment is a measure of the polarity of a molecule. The more polarized the bond, the higher will be the dipole moment. Now, if you look at hydrogen fluoride, HF, is a molecule. Hydrochloric acid is a molecule. Hydrobromic acid, HI, these are molecules. So the dipole moment of hydrochloric acid, the molecule hydrochloric acid, is 1.1. The dipole moment of the molecule HF is 1.7. The dipole moment of the molecule HI is 0.4. But we do not have a molecule called HC or a molecule called carbon N. We do not have such molecules. But these ones, what they are measuring the dipole moment of the individual bonds. The hydrogen-carbon bond, dipole moment of that is 0.4. For example, in methane, we have 4 carbon-hydrogen bonds. And then the dipole moment of each of the 4 carbon-hydrogen bonds is 0.4. Okay, but in some molecules, they only have 1 chemical bond. So therefore, in such type of molecules, the bond moment and the dipole moment are the same. The bond moment of the hydrogen-chlorine bond and the dipole moment of hydrochloric acid are the same. So that's why this is said in a molecule with only 1 covalent bond, the dipole moment of the molecule is identical to the dipole moment of the bond. In a molecule with only 1 covalent bond, the dipole moment of the molecule is the same as the dipole moment of the bond. For example, the dipole moment of hydrogen chloride, HCl, is 1.1 dpi, because the dipole moment of the bond, the hydrogen chlorine bond, is also 1.1 dpi. But the dipole moment of a molecule, which has got more than 1 covalent bond, the dipole moment of the molecule depends on the dipole moment of all the different bonds taken together, as well as the geometry of the molecule. Okay? Now, I don't know how much physics you have done in high school. Did you study about vector quantities and scalar quantities?
Yes.
Anyone who has not heard of those words?
We had them.
Anyone who has not heard?
Yes.
You have not heard of them, isn't it?
Yes.
Okay, I will explain. Okay, for both of you.
Heard of them.
Yes. So let me
we
just
have
explain.
them.
Let me just explain what the difference between vector quantities and scalar quantities are. Okay, the quantities, the physical quantities, which you can quantitatively measure for a substance, they can be vector quantity or scalar quantity. Let me just give you an example. If you have 2 kilos of sugar, 2 kilos of sugar, please mute. And then you put this 2 kg of sugar in a weighing balance. Okay? And then you bring another 3 kilo of sugar and put on the same weighing balance. What do you think will be the total weight of the sugar? You have 2 kg of sugar in the weighing balance, and then you brought another bag that has got 3 kilograms of sugar, and you put it on the balance. What will be the total weight? The total mass?
5.
It will be
5.
5. Does it matter? Does it matter? Does it matter on how you put the sugar on the balance? One of them you put it
No.
facing up, the other facing down. Does it matter?
No.
No. Such kind of physical quantities. Said you are with a whole family. Such kind of physical quantities which do not depend on the direction are called scalar quantities. Now let me give you another example of a quantity which we can measure, which is different from mass, a vector quantity. A simple example of a vector quantity which we can easily relate to is force. Force. Okay? Suppose you have probably a table in front of you. Okay? And then you and your brother or sister put some force on this table. Okay? So if both of you are applying force of 5 newtons on this table, and you are putting the force in the same direction. You are both in the same direction of the table, and then you are pushing it. What will be the net force that is applied on that table? Each of you have applied 5 Newton force, and then you are applying this force in the same direction. What will be the total force that's applied on the table?
10 newtons.
10 newtons. However, you are on this side pushing the table with 5 Newton force, and then your brother or sister from the other side is pushing the table on this side. You are pushing it this way with 5 Newton force. Your brother or sister on the other side is pushing it the other way, from the other side with the same force. What will be the net force on the object, on the table?
0.
Zero work.
0.
Yes, it's like somebody want to take away a table from you, from your office, from your bedroom. You are pushing it, and then the other one will say it's tacky, and pushing it the other side. The table is not going to move, isn't it?
Yes.
So what you can see from here, there are forces that are applied. People are sweating. You are pushing it with 5 Newton force on this side. The other one is pushing. You are sweating, but no effect. So force depends not only on the magnitude, but also on the direction. So we have vector quantities. These are physical measurable quantity that depends on magnitude as well as direction. So we have 2 types of quantities: vector quantities and scalar quantities. scalar quantities that don't depend on the direction, just magnitude. 2 kilo of sugar plus 3 kilo of sugar is 5 kg of sugar, but 2 Newton of force and 2 Newton of force might be 4, might be 0, might even be another value. It depends on the direction, okay? So now, dipole moment is a vector quantity. So, dipole moment is a vector quantity. Let me just give you so that you can work with me. Remember, we said that the bond moment of the hydrogen-carbon bond is 0.4. Please mute. The bond moment of the hydrogen-carbon bond is 0.4. 0.4. Each of the hydrogen-carbon bond, the bond moment of a hydrogen-carbon bond is 0.4. In methane, which is CH4, we have 4 carbon hydrogen bonds. Each of the bonds has a bond moment of 0.4. If dipole moment was a scalar quantity, the dipole moment of the CH4 molecule, which has 4 carbon hydrogen bonds, would have been 4 times 0.4, 1.6 dBi. If dipole moment was a scalar quantity, you just add or multiply them. 4.4, 0.4 plus 0.4 plus 0.4 plus 0.4 will be 1.6. But I'm sorry to tell you, the dipole moment of methane is 0. 0. How is it possible for the dipole moment to be 0 when there are 4 bonds that are polarized? It is like the case where you have the 2 people pushing the table, but they are pushing it in different direction, canceling out each other. In methane, we have 4 carbon hydrogen bonds, which are polarized. Methane has a polarized bond, but the molecule methane is not polar. The dipole moment of methane is 0. Can you tell me how it can be 0? And why it should be 0?
Yes.
So try.
Yeah, it is 0 because every bond adds its own dipole moment and they are pulling it in different directions.
They are pulling it or pushing it in different direction, isn't it? Cindy, that's why they cancel
Yes,
out.
they cancel each other, so it becomes 0.
So for example, you see, like you remember, we show the polarization of a bond in 2 ways, okay? When you have a bond that's polarized, we show it in 2 ways, putting partial positive and partial negative. So if you have a chemical bond between carbon and hydrogen, carbon is a bit more electronegative than carbon. Carbon is a bit more electronegative than hydrogen. The electronegativity of carbon is 2.5. That of hydrogen is 2.1. 2.5 minus 2.1 is 0.4. Okay? So on the carbon, you'll have partially positive charge. On the hydrogen, you'll have partially positive charge. On the carbon, you'll have partially negative charge. Since carbon is a bit more electronegative than the hydrogen, carbon will pull the electrons of the hydrogen-carbon bond towards itself more than the hydrogen would. So on the carbon, we'll have excess of electron. On the hydrogen, we'll have deficiency of electron. On the carbon, we put partially negative charge. On the hydrogen, we put partially positive charge. This is one way of showing the polarization of a bond. But the other way of showing the polarization of the bond is the crossed arrow. Okay? So this crossed arrow has sense of direction. It is going from the less electronegative element to the more electronegative element. It is pointing from the partially positive center towards the partially negative center. So the crossed arrow will point from the hydrogen to the carbon. Okay? Is it clear?
Yes.
Hello?
Yes.
Now you remember methane is sp3 hybridized.
Yeah.
The shape of methane is tetrahedral, okay? You have the carbon, and then the 4 hydrogens that are attached to this carbon, they point to the corners of a tetrahedron, very far away from each other, okay? So on this methane, you have these 4 carbon hydrogens, which are pointing towards the corners of a tetrahedron. All of them are separated by 109.5 degrees. Then when you look at each of the bonds, they are polarized such that the carbon is partially negative, the hydrogen is partially positive. So the polarization of the bond is from the hydrogens to the carbon. So you have a crossed arrow that will be pointing from the hydrogens to the carbon, from the hydrogens to the carbon, from the hydrogens to the carbon. As you can see, they are pointing in the same direction. They are pointing towards the carbon, okay? It's like you have a table, then you have 4 people applying force on it. And then these 4 people are applying force at an angle that points towards the center, and they are pushing it towards the center. Will the table move? If the forces are the same, but they are all of them applying force towards the center, will the table move?
No.
It will not move. So this is what basically is happening in the case of methane. The 4 carbon hydrogen bonds, the way they are polarized is from the hydrogen towards the carbon. All of them are pointing towards the carbon, and their effects cancel out. And then we have, despite the fact that methane has 4 carbon hydrogen bonds that are polarized with certain bond moments, in this case, a bond moment of 0.4 dBi each, but because of the way they point towards each other, they cancel out. So what determines the most important point? What determines the polarization of a bond? I mean, a molecule, whether a molecule is going to be polar or non-polar, or how polar is going to be, is 1, the bond moments of the individual bonds, as well as the shape or the geometry of the molecule. You have to take the bond moments of each of the bonds, as well as the geometry of the molecule and the direction in which these bond moments face. If they enforce each other, there will be a net dipole moment. If they cancel each other, there will be no dipole moment, or the dipole moment will be less. Let me just give you an example, okay? Anyway, a polar bond has a dipole. That's what it means. It has got a negative and a positive end. The size of the dipole moment is indicated by the dipole moment, which is given the Greek letter mu, and the dipole moment of a bond is equal to the magnitude of the charge on the atom, be it positive or negative, times the distance between the 2 charged species. Let me just give you using an example. Let me explain this using this expression. Suppose you have a bond between 2 elements, a a polar bond between two elements, a polarized bond between two elements. So one of them will be partially positive, the other one will be partially negative. Then at the end of the day, there will be a charge that's going to be developed on these two atoms. The charge on one of them will be Q plus, the charge on the other will be Q minus. In terms of magnitude, the charges on the two atoms that are involved in covalent bonding are the same, except that one of them has excess of electron. Then by the amount, by the much, one of them will have excess of electron, the other one will have deficiency of electron by the same magnitude. As a result, the charges that will be developed on the two atoms in terms of magnitude, they are the same. What is different, what the difference is in terms of the magnitude, the charges, one will be positive, the other one will be negative. So if you have a polar covalent bond between two elements, one of them will be partially positive, the other one will be partially negative. One of them will have a Q plus charge, the other one will have a Q minus charge. The Q representing the magnitude of the charge, and the plus and the minus indicating that this is electron deficient and the other one is electron rich. And suppose the distance between them is R. The length, the bond length between them is given as R. Now, the dipole moment of this particular bond is the charge times the distance. Dipole moment is Q times R. Remember what I told you. Dipole moment is a measure of the polarity of a bond or a molecule. It measures polarity. And then polarization of a bond depends on two factors. One of them is the difference in terms of electronegativity between the atoms. The other factor is the size. So Q will be more if the difference in electronegativity between the two atoms is more. Q will be small if the difference in electronegativity between the two atoms is small. Okay, so Q is a measure of the differences in terms of electronegativity between the two atoms. The other factor is R. R is the distance. So the more the bond length, the more will be the dipole moment. But the bond length between two atoms is measured in terms of angstrom units, is very small. It is a contribution towards the dipole moment is not very significant, but all the same, it contributes. Okay, that's why I was telling you dipole moment, or the polarization of a bond or the difference between two elements depends on two factors. One of them, differences in terms of electronegativity. The other one is the size. Because if this one is big, for example, if one of the atoms is big, the distance between them is going to be big. As a result of that, the dipole moment is going to be big. So dipole moment depends on two factors, and this is shown in the equation. Okay, now the polarity or dipole moment of a molecule is the vector sum of the dipole moment of each of the individual polar bonds. You have to do a vector sum. And then when you do vector sum, you take into consideration magnitude as well as direction. Okay, now as a result, if you look at carbon dioxide, let's look at carbon dioxide. In carbon dioxide, we have two carbon-oxygen bonds. Two carbon-oxygen bonds. This is the structure of carbon dioxide. You have a carbon double bond oxygen, carbon double bond oxygen with a lone pair of electrons on each of the oxygen. If you draw the Lewis structure of carbon dioxide, this is what you get. You remember, Lewis structure does not give us information about the geometry or the shape of molecule. All it tells us that the carbon is at the center, and then it is bonded to 2 oxygens. And then when you write the Valley-Lewis structure, you will see the carbon forming 2 double bonds with the oxygens, having 2 lone pair of electrons on each of the oxygen. It does not tell you any information about the shape of the molecule. But what gives you information about the shape of the molecule is the hybridization. Now, can you tell me what the hybridization of this carbon is? What is the hybridization of the carbon of carbon dioxide? Huh?
sp2.
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 Anybody who disagrees? If
It's not sp2.
what is it?
It is sp.
SP. Now tell me, why is it SP? I agree with you, it is SP. Now tell me why it is SP.
Because the bond angle is 180.
But why is it 180, not 120?
Because
It forms a linear bond.
linear.
Because
It's linear.
Linear.
why is
From
it
a
linear?
linear bond.
Why is it not planar? So see, like, if, of course, you see double bond, okay? And then I've told you, when you see a double bond, the hybridization is sp2. If the hybridization of the carbon dioxide, the carbon in carbon dioxide was sp2, the shape of carbon dioxide would have been different. You have carbon and 2 oxygens down, one of the oxygen down, the 2 double bonds separated by 120 degrees. It would have been something like that. But that's not the case. The hybridization of the carbon is sp. Now, why is the hybridization of the carbon sp when you can see the carbon is involved in double bond? Okay, now the other way which you can easily answer is in a carbon-carbon double bond or in an sp2 hybridized system, we only have 1 pi bond to which the atom is bonded with the other element. There will only be 1 pi bond. But on the carbon, how many pi bonds does this carbon have? This carbon.
2.
2. A pi bond with this oxygen and a pi bond with the other. That carbon has got 2 pi bonds. You remember, in a triple bond, we have 1 sigma bond and 2 pi bonds. Okay? Then a triple bond is sp2 hybridized. The shape is linear. So this carbon, since it is involved in 2 pi bonds, since it is formed 2 pi bonds with other element, its hybridization is sp. sp means the bond angle is 180 degrees. The molecule is linear. Okay, now let's look at each of the carbon oxygen bond. We have agreed the shape is linear. These ones are found in a straight line. Now let's look at the polarization of each of the carbon oxygen bond. Forget about the other oxygen. Let's look at this carbon oxygen bond. Here you see a chemical bond between carbon and oxygen, between 2 different elements, between the second most electronegative element, oxygen, and carbon. So between carbon and oxygen, which one is more electronegative?
Oxygen.
So if you draw a cross arrow, the cross arrow will start on the carbon and point towards the oxygen. like this. The same on this side. As you can see, there are two polarized bonds in carbon dioxide. One is pointing this way, the other pointing the other way. And these ones, they cancel out each other. Then as a result, the dipole moment of carbon dioxide is zero. Zero. Carbon dioxide is a non-polar molecule. If carbon dioxide was not neutral, I can assure you carbon dioxide would have been a liquid. But carbon dioxide is a very low boiling gas because it is linear and its dipole moment have cancelled out that as a net dipole carbon dioxide is non-polar. What it basically means, there will be no force of attraction between one carbon dioxide molecule and another carbon dioxide molecule. Because in the carbon dioxide molecule, there is no center that is partially positive and partially negative. It is all cancelled out. It is a neutral molecule. So you should not expect a force of attraction between two neutral molecules. Carbon dioxide is a small molecule. It is non-polar. It is neutral. So the force of attraction between two carbon dioxide molecules is non-existent. So carbon dioxide is a gas. Okay? And soon we'll look at water, okay? Water, what is the boiling point of water?
100.
A very highly boiling liquid. What this is telling us, there is a strong force of attraction between two water molecules. From here, you can easily tell that water cannot be a linear molecule. If water is linear, we have oxygen, hydrogen towards the left, another hydrogen towards the right. In terms of polarization, hydrogen is more, oxygen is more electronegative than hydrogen. So the bond moment will be from the hydrogen to the oxygen, from the hydrogen to the oxygen. Both of them point towards the oxygen. They will cancel out. Water will have zero dipole moment. But water is not a linear molecule. Water is a bent molecule. We'll discuss that one, okay? So when you measure dipole moment of a molecule, you have to take into consideration the bond moments of the individual bonds that contribute to that particular molecule, but also the geometry of the molecule, which will tell you in what way these bond moments are arranged, in which direction are they pointing? Are they reinforcing each other or are they cancelling out each other? As you can see, in the case of carbon dioxide, despite the fact that we have a very polarized carbon-oxygen bond, the molecule itself is non-polar because of the direction in which they point. So totally cancelling out each other. So carbon dioxide is non-polar. Therefore, for molecules that have more than one covalent bond, the geometry of the molecule must be taken into account because both the magnitude and the direction of the individual dipole moment, the vector sum, determines the overall dipole moment of the molecule. As a result, symmetrical molecules therefore have no dipole moment. If you look at carbon dioxide, is a symmetrical molecule. If you put a mirror in the middle across the carbon, this side and the other side are the same. It's a symmetrical molecule. Symmetrical molecules will have zero dipole moment. Another molecule, which we can see as an example, is carbon tetrachloride, where you have carbon that has formed single bonds with 4 chlorine atoms. Since the carbon has formed single bonds with 4 atoms, the hybridization of the carbon is sp3. The arrangement of the 4 chlorine atoms is towards the corners of a tetrahedron. They point towards the corner of a tetrahedron. They are separated by the same degree of 109.5, 109.5, 109.5. And then when you look at each of the carbon-chlorine bonds individually, chlorine is more electronegative than carbon. Electronegativity of chlorine is more than that of carbon. So the bond is polarized, and then we show the polarization of the bond using a crossed arrow that points from the less electronegative atom, carbon, pointing towards the chlorine. So we have these 4 bond moments. As you can see, they are all pointing in the same direction away from the carbon. The magnitudes are the same. They are pulling the carbon in 4 different directions with the same vigor. As a result, the dipole moment of carbon tetrachloride is 0. It has got 0 dipole moment. However, the moment you change one of the atoms, for example, if I have hydrogen here, and then if I make one of them to be chlorine, as in the case of this one, as in the case of here, the situation changes. Because in this particular case, the bond moments were in opposite direction. But when it comes to this one, it's different. Here, of course, this is the carbon-chlorine bond. Chlorine is more electronegative than carbon, so the bond moment goes from the carbon to the chlorine. How about the hydrogen-carbon bonds? Hydrogen, between hydrogen and carbon, hydrogen is a bit less electronegative than carbon. So the bond moment will be from the hydrogen to the carbon, from the hydrogen to the carbon, from the hydrogen to the carbon. As you can see, all of them, the chlorine is pulling it that way, and then these hydrogens are pushing it that way. They are reinforcing each other. As a result, this molecule is a polar molecule because it has got a net dipole. So the dipole moment of this molecule is 1.87 dBi, more than the bond moment of the carbon-chlorine bond. If you remember, the carbon-chlorine bond, the bond moment of the carbon-chlorine bond, the carbon-chlorine bond is 1.5, okay? 1.5. But the dipole moment of this molecule is 1.87, more than 1.5, because the hydrogen carbon bonds, they are contributing towards it. Okay, some of them, some of the bond moments of the hydrogen carbon bond are canceling out, but there are some that still remain. So the dipole moment of this molecule is 1.87. It is not 1.5 plus 0.4 plus 0.4 plus 0.4, giving us a dipole moment almost greater than 3. It is not. It is only 1.87. Can you tell me why it is not 1.2 plus 1.5? Why it is not 2.9? Instead, the dipole moment of this molecule is only 1.87. Why do you think this is the case?
I think
I know. Okay.
the carbon-hydrogen bond cancels each other, hence remaining with the carbon-chlorine bond and the carbon-hydrogen bond, which brings 1.9.
Because they don't completely cancel out. That's why the dipole moment of this molecule is more than 1.5. They contribute some, but let me give you a scenario. You remember, if you have an object on the table where you are, okay, if you lift this object, if you lift it up, it will move upward, isn't it? It will be lifted. It will be vertically lifted. Then you put back the object, and you pull it horizontally, it will move horizontally, isn't it? But if you lift this object at an angle, two things will happen. The object will be lifted up, it will move vertically, it will also move horizontally. So for example, you have an object a bit further away from you, and then you stretch your hand and you lift it at an angle. When you do that, the object will have come towards you, it will also be lifted up. So when you have such a force at an angle, this force will have two components, vertical and horizontal components. So when you have these ones, we have, since this is at an angle, you have a vertical component and a horizontal component. Just let's look, just concentrate on this hydrogen, okay? So this, the bond moment of this will be resolved so that we have a vertical component that points up and another component, a horizontal component that points this way. When you look at this hydrogen, it also has a vertical component that points up and a horizontal component that points this way. What I want you to concentrate on is on the horizontal components. Are the horizontal components of the bond moment, are they reinforcing each other or are they canceling each other?
They are reinforcing each other.
Reinforcing or canceling? The horizontal ones. You have not understood. Okay, let me say it again. Okay, you have this hydrogen carbon bond. Okay, this hydrogen carbon bond, it is at a certain angle. Okay, it's just like lifting an object at an angle. When you lift an object at an angle, this object will be lifted up and sideways. It will be lifted vertically and horizontally. It will move vertically and horizontally. So when this bond moment, when you resolve the effect of this bond moment, it will have two effects. It will have a vertical one pointing up, just like the carbon-chlorine bond, like that. It also have horizontal component that points towards the carbon like this. Then when you look at the other one, it also have a vertical component which points up, adding its component towards the polarization of the molecule, but the other one is pointing towards this. So we have two horizontal components that are both of them pointing towards the carbon in opposite direction towards the carbon, canceling out each other. That's why, despite the fact that we have 4 carbon hydrogen bonds that should potentially contribute each of them 0.4 towards the dipole moment of the molecule, some of them they cancel out. That's why the dipole moment of this is less than the total sum of the bonds. Anyway, let me stop here. I want you to think about this, why the dipole moment of this molecule is not 1.5 plus 1.2, 2.9. Why is it 1.87 instead of 2.9? I want you to think about it over the weekend so that when we discuss next week on Wednesday, you'll be in a better position to understand it better. Okay? So I wish you a nice weekend. See you next week.